get started. It's my pleasure. Let's get started. It's my pleasure to introduce Mani. All of you know him pretty well. This is the first time in my life I'm seeing him wear a suit. And that, I think, is going to be the reaction for pretty much everyone in this room. What I found out was that this was made for him by the Indian government 10 years ago, because he was representing India in an Olympiad and he didn't have a suit, so they got one made for him. The takeaway for me really is that clothes from 10 years ago still fit him. For me. So, no, more seriously, I think Mani has been, if you will, my most thoughtful and persistent student. And the reason I say that is he's working on a problem that some of you know has been looked at, as like literally thousands of papers on this problem for 20 years. Victor, I think your first reaction also was, why are you working on this, right? And he stayed at it, he persisted, and I think he's produced something truly groundbreaking. I think he's really pushed the envelope. I think this is probably the best positioning system out there. It was my privilege to advise him. I think you'll like the talk. Let's take it from here.
Thank you, Sachin. And thank you all for being here today. So, today I'm going to talk about the world's state-of-the-art wireless positioning system that can deliver centimeter-level accuracy using commodity radios. And the surprising insight that I will be building upon is that instead of fighting nature, I'm actually going to leverage the destructive effects of nature that were previously considered as only harmful. No one in this room is going to disagree that positioning has been a fantastic primitive. A ubiquitous outdoor positioning system like GPS has completely transformed our lives. If we can achieve centimeter-level accuracy, a ubiquitous indoor positioning system will revolutionize several applications from virtual reality to medical implants. Of course, it is no wonder that developing such a system has been the holy grail of wireless sensing research. But the shocking thing is, despite 2 decades of active research, a practical yet accurate wireless positioning system has always been elusive. Today, I am going to show an accurate wireless positioning system that can deliver centimeter-level accuracy and that does not impose any sort of restrictions. It requires no hardware modifications like adding more antennas to your device. It requires no additional infrastructure than what is required for regular wireless communication. It requires no modifications to the protocols or the way we communicate. You get the idea. In fact, what all it requires is a standard wireless chip that you can go buy in a retail store and a publicly available software tool to query the wireless channel that is anyways calculated by every wireless chip for every transmission that it listens to. That's it. This has been possible because of a fundamental change in the philosophy of how we build wireless positioning systems. Now, the traditional thinking says that we have to position the target device by overcoming the distortions introduced by all the reflectors in the environment, like walls, tables, furniture, the things that we have no interest in. Today, I'm going to introduce a new philosophy to harness these reflectors themselves to make the practical systems accurate. I call this approach to harness the naturally available reflectors as Synthetic Aperture Radio. For the audience who are actually familiar with the radar literature, this notation is like an intentional throwback to the Synthetic Aperture Radar concept that has been around since like 1950s, and it is like a philosophical ancestor to my work. The things are going to get even more interesting. What I'm actually going to show you is that harnessing nature will not only make the systems practical, but it will dramatically improve the accuracy. In fact, Synthetic Aperture Radio enabled the first centimeter-level accurate positioning system using commodity radios. Over the past 5 years, I have developed several useful systems by building upon this concept. So I developed a practical indoor navigation system by using cheap, off-the-shelf Wi-Fi radios. I developed a virtual reality positioning system using the same Wi-Fi chips. This has been a very exciting work as it created a nice bridge between the wireless technology and computer vision applications. I moved on to building a real-time positioning system using a single Wi-Fi device for tracking virtual reality accessories like mind controllers. And one really surprising system that I built was a positioning system for resource-constrained devices. like pill bottles or even your keychains. Now these devices, they cannot transmit active wireless signals because they are constrained in power. But still, they can be positioned using the same ubiquitous wireless infrastructure. Let me actually give you a quick demonstration to give you a taste of the systems that I have built. Here to the bottom right, we see the actual physical movement of a Wi-Fi chip. The Wi-Fi chip is attached to a device that collects the ground truth trajectory by using specialized hardware. Now the top right shows the trajectory estimated by using Wi-Fi signals, and the top left shows the actual ground truth trajectory. Here we can clearly see that the trajectory estimated by using Wi-Fi signals closely resembles the ground truth trajectory. The error in recreating this particular trajectory was less than a centimeter, and I achieved this using nothing but standard wireless chips, no modifications whatsoever. This is especially impressive when we consider the fact that any wireless positioning system working within the confines of small bandwidth, small antenna arrays, no fingerprinting, could at best achieve an error of roughly like 2 meters. Before getting into the mathematical details about how I built these systems, I would like to give you a brief overview of the challenges in building a practical positioning system and how synthetic aperture radio overcomes these challenges. The working of any wireless positioning system can be described in a very simple manner. Transmitters like these Wi-Fi routers, they transmit wireless signals. And a target device like this virtual reality headset figures out the directions of the signals coming from each of these routers and uses those directions to find its location. Now life would have been pretty easy if these routers and the virtual reality headset were the only objects in the environment. But we are surrounded by reflectors like walls, TVs and bookshelves, and the signal that is reflected from these reflectors is going to correct the signal coming from the router. This phenomenon is called as multipath, and multipath introduces positioning errors. In fact, successfully separating out the signal coming from multiple paths is the biggest challenge for any wireless positioning system. This multipath is like the Darth Vader of wireless positioning research. It is the evil that every positioning system has to fight against. Now, if we look at both these paths, you can see that the signal is traveling along different directions and it travels for different distances. And the approaches to decouple these paths uses these two insights. So, people used a ton of antennas to decouple the signal according to the different directions the signal is coming from. However, in order to separate the signal with a resolution of 1 degree, you need as many as 200 antennas separated by like half wavelength distance. People also used multiple gigahertz of bandwidth to separate the signal according to the different times at which the signal reaches the receiver. However, in order to separate the signals with a resolution of 1 centimeter, you need as much as 30 gigahertz of bandwidth. However, all these approaches couldn't be farther from being practical. The reality of everyday wireless devices, whether you are using Wi-Fi, Bluetooth or cellular systems, is that they have at best 3 to 4 antennas and few tens of megahertz of bandwidth. What if I told you that you could get as many antennas as you want without actually having to build huge antenna arrays? The insight is pretty simple. Things move in real world, whether it is a robot or a human wearing a virtual reality headset. And I'm going to show you today how we can treat these measurements obtained from different positions as if they are obtained from a single giant antenna array, which we call as synthetic antenna array. What this means is that we can get the benefits of a large antenna array while working with our everyday wireless devices with small antenna arrays. Now this simple to articulate insight seems to solve our problem, but creating this antenna array abstraction from the measurements at different positions, is it going to be that simple? I mean, if I simply collect measurements from 100 positions using this simple device, is it equivalent to collecting measurements from a 300 antenna array? Of course there is a catch here. So let us actually play a simple spot the differences game to understand this complexity, and I want you to participate. So here to the left, we see a physical antenna array obtained from assembling a large number of antennas. And to the right, we see a synthetic antenna array obtained from measurements at different positions as the device moves. Now there are two differences between these two setups. Can anyone in the audience actually spot these differences?
Is it a test for the committee?
No, it's not.
I already know because you and I have talked about it, so it's not fair for me to say which is why it's not a task for the committee.
Alright, so actually, in a physical antenna array, you know the distances between different antennas on your device because you have assembled the device, right? Now, in a synthetic antenna array, you do not know how the device is moving. So you do not know how these antennas are placed with respect to each other in this synthetic antenna array. There is one more difference. In a physical antenna array, all the measurements are obtained at the same time. However, in a synthetic antenna array, the measurements at different positions are obtained at different times. Now, both these assumptions that you know the antenna array geometry and that all the measurements are obtained at the same time form the very core of how antenna arrays work. This is because if you do not know the antenna array geometry, then there will be infinitely many possible values for the target device position that will satisfy the antenna array equations. Similarly, it is critical that all your measurements are obtained at the same time because the hardware introduces different random distortions for the signals obtained at different times. For example, oscillators used in these devices corrupt the wireless signals obtained at different times by adding something called as phase noise. See how the distortion is modeled as noise, so it is going to be pretty random. So these two challenges of unknown motion and the unknown random time-varying hardware distortion are the primary reasons why it is an extremely hard problem to create a synthetic antenna array abstraction using communication radios like Wi-Fi. And again, for the audience who are familiar with the radar literature, these two challenges are also the reason why this is a much different and a much difficult problem than the traditional synthetic aperture radar concept that has been around since like 50s. Now, so how do we create this antenna array abstraction from the measurements obtained at different positions at different times? First, we need to be able to estimate the displacements over time so that we can figure out the antenna array geometry. There is something even worse hiding here though. We need to somehow correct for the random time-varying distortions. And this is a very, very hard problem because we really have no idea what these distortion values are, nor can we predict them as they are completely random. So, how do we solve this problem? Remember those reflectors, which are the undesirable distorters of the signal coming from our beloved target device? The insight is that the hardware distorts the wireless signals along any of the paths in the very same manner. This is because the distortion is introduced in the hardware, not during the actual wireless propagation. So the signal from each of the reflector is going to carry a copy of this hardware distortion and allows us to compensate for the distortion. So turns out that behind all that evil exterior, multipath is not so evil after all. We just need to be able to see it in a whole new light. By the end of the talk today, I would really like to convince you that multipath is our Adam. And harnessing the reflectors that are naturally present in the environment and harnessing the motion that is naturally happening on the device is the way to build practical positioning systems with limited bandwidth and small antenna arrays. Now let us get into some mathematical details about how this algorithm is working. Let us start with how antenna arrays work. Time of flight, which is the time taken for the signal to reach the receiver from the emitter, is going to be slightly different for different antennas on your device. Now this change in time of flight can be represented as a projection of the distance vector d between the antennas on the unit direction vector of the incoming signal r. And this change in the time of flight creates a phase change across these two antennas, which is directly proportional to the time of flight change. Specifically, the proportionality constant is 2 pi times the frequency f. And the signal that is obtained at any antenna is the sum total of the signals from all the paths in the environment. So here I am just showing a single reflector for simplicity, but just stay with me. Here there are two paths. Alpha 1 and alpha 2 are the complex attenuation of the signal along both these paths. R1 and R2 is the direction of the incoming signal along both these paths. What we can see here is that the phase of the signal along each of these paths and the direction of each of these paths is encapsulated in this complex exponential term. And it is not really easy to separate out the signals coming from different paths and to recover the direction from both these paths. We can actually show that it is a hard non-convex problem. However, we can use a class of algorithms called as super resolution algorithms that will successfully resolve the signal coming from different paths and help us recover the directions of these two paths as long as the number of measurements or equivalently the number of antennas on our device is greater than the number of variables in the system or equivalently the number of paths in the environment. And now that's a problem because due to size and cost limitations, unless the device is like a airport security scanner or like a military radar, the number of antennas on our everyday wireless devices has always been limited to 3 to 4 antennas. But we are surrounded by way more reflectors. Just look around you. So my quest in grad school, if it has to be summed up in like a single sentence, it would be something like, how do we actually disentangle this multipath without the benefit of huge antenna arrays? I was a first year grad student when I got introduced to this positioning problem and antenna arrays, and I had a pretty simple realization that was not yet implemented in practical systems. So all these communication systems like Wi-Fi, they transmit signals on multiple frequencies. And each frequency provides us with an additional measurement while the number of paths in the environment remain the same. So I developed this system SpotFi by using this insight that uses the antennas and frequency measurements together. I deployed it on a floor in our department, this exact floor in Packard. This is what we are seeing here. And the system demonstrated an error of 0.4 meters. Just to put this number in context, the previous state-of-the-art system used as many as 6 to 8 antennas like these to achieve similar accuracy. So it is pretty useful to be able to achieve such accuracies by using just 3 antennas which are available in our commodity radios. So we submitted a paper, I was pretty happy, and then a week later this happened. So I experienced virtual reality for the first time in a Stanford industrial exhibit. So no commercial version of virtual reality headset was available as yet back then. Now I cannot show you the exact experience that I had that particular day, but it was something like this. There was a specialized device, something like this, that was placed in the arena, and that was placed there just to track the virtual reality headset. And there was this 1 meter by 1 meter square that was drawn on the carpet, and you are allowed to move only within that box. And this was because of the limitation of the positioning system. I was like, positioning can't be so cumbersome. Can I just use my Wi-Fi systems for virtual reality positioning? But applications like virtual reality require way better accuracy than few tens of centimeters. And if we can somehow get even more measurements, we can push this accuracy even further. And this is when I realized that we do not need to limit the number of antennas at all. That is just an artificial limit. All these applications, all these devices, they are naturally moving anyways, creating these measurements from diverse positions. What all we need to do is to somehow combine these measurements from multiple positions and create this antenna array abstraction. And in order to do that, as we saw before, first we need to estimate the displacements over time in order to figure out the antenna array geometry of this synthetic antenna array. And for this problem, this is the scene that we are going to stick with. So there is a Wi-Fi router transmitting Wi-Fi signals. There is a Wi-Fi receiver on the virtual reality headset listening to those signals. As the device moves, the time of flight from the router to the headset is going to change. And our goal is to recover the trajectory delta as the device moves. Now, as we saw before, as the time of flight changes, the phase at any particular antenna is going to change. And the proportionality constant is given by 2 pi times the Wi-Fi frequency f. Now, Wi-Fi uses 5 gigahertz signals. What this means is that even if the time of flight changes by few picoseconds, it still registers a significant change in the phase of the received signal. this translates to saying that the phase is actually sensitive to position information with sub-millimeter level resolution. That is a good news, but we cannot directly use the phase information across multiple transmissions to recover the time of flight information. And there is a very good reason for that. That's because the change in the time of flight is corrupted by the change in the clock offset. And this change in clock offset was the hardware distortion that I was talking about. So what do I mean by this? In any wireless system, the transmitter and the receiver are separate devices. Because these devices are separate, they have their own clocks. And these clocks drift over time in their own random fashion. So this creates a clock offset between the transmitter and the receiver. And the worst part is that this clock offset actually changes with time. So as the device moves, the time of flight is changing not only because of the motion of the device, but also because the clock offset is changing. Interestingly, look at the scales of these changes. Like the time of flight change due to typical human motion between successive wireless transmissions is on the order of like few tenths of picoseconds or like few millimeters. However, during the same time, the clock actually drifts by few tenths of nanoseconds. So what this means is that the distortion that you are introducing into the system, which is a clock offset change, is like 1,000 times larger than the signal that you are trying to measure, which is the time of flight change due to the physical motion. Now the phase of the signal due to these two components are obtained by simply multiplying those components by 2 pi times the frequency f, and the overall received signal at any particular antenna across transmissions is the sum total of these two components. So the overall perceived phase at any antenna is composed of two components that are coupled to each other. One due to the motion and the other due to the clock offset change O. And these are inseparable, as you can see here. And this brings us to the observation that the two challenges in building a synthetic aperture radio, which is the unknown motion, delta, and the unknown clock offset change, O, they are inseparable, they are coupled. And in order to estimate the displacement, you need to somehow estimate the clock offset change. You need to know the clock offset change. And knowing this clock offset change is a very, very hard problem. My initial instinct was, okay, let me try and predict this clock offset change by modeling the clock drift. I spent months fitting various regression models, applying time series filters like Kalman, but the residual error in estimating, in predicting this clock offset change was still unusably large. And I started having these nice looking Gaussian distributions for the residual errors, and at this point I started thinking that, you know what, maybe we cannot predict clock offset change with sufficient accuracy. Maybe we need some other way to differentiate the motion and the clock offset change. And this is when it struck me, these reflectors, like these multiple paths, like if you look at the time of flight of the signal along different paths, it is different because the direction of the signal is different for different paths. However, the phase change along any of the paths is corrupted by the same clock offset in the same manner. So this actually, however random this clock offset change or the phase noise may be, we are essentially getting multiple copies of that randomness because of the multipath. So in some way, although the reflectors are the primary reason why the problem is so hard in the first place, they are actually necessary for us to actually eliminate this clock offset change. So I think they are just like a true embodiment of necessary evil, just like taxes, you know. Now that we have this insight, let me sum up the positioning algorithm. I have to inform you though that the coming 3 slides are not for a complete detailed understanding, but to give you a glimpse of the iterative algorithm that I developed based on this insight. We can actually, once we have this insight, we can actually think about like multiple approaches to solve this problem. So, and I strongly encourage the audience to refer the CVPR paper for more details. So, what I'm going to do is that I'm going to apply the super resolution algorithm for each wireless transmission separately to get an initial estimate of the directions of both the paths, R1 and R2, and the phase of the signal along both these paths. Now, if I look at the change in the phase of the signal across two transmissions for any two paths, then voila, the clock offset term disappears, and we know the rest except for the trajectory delta, which is of our interest anyways. What we can notice here though is that each set of two paths provides us one equation in terms of the underlying trajectory delta. But the trajectory is a three-dimensional quantity. So what I did was that I used two paths from each Wi-Fi router to get one such equation in terms of the underlying trajectory delta. And I used multiple such routers to get multiple such equations in order to solve for the displacement. Now, once I have this estimated displacement and estimated clock offset values, I can substitute those across the wireless transmissions obtained across multiple transmissions and apply super resolution algorithm on all these transmissions together on this large synthetic antenna array to get very accurate estimates of the directions, which I can then use to find my location very accurately. So, how well does the system perform? In order to measure that, I use this particular setup where I developed the system using Intel 5300 Wi-Fi chips. Now, these are commodity retail chips that you can buy in a retail store. The reason I chose those chips is that they have a publicly available API to query the wireless channel. So this helps in like making the system perfect. So I attach this Wi-Fi chip to an Oculus DK2 virtual reality headset. The Oculus requires this camera to be placed within 1 to 2 meters to be able to capture the ground truth trajectory. However, the Wi-Fi access points that are locating the target, they are located much farther away at the corners of a 6 meter by 6 meter room. And I conducted 100 experiments where I continuously moved the headset along with the rigidly attached Wi-Fi chip to create trajectories like this. And the system actually demonstrated sub-centimeter level error in recreating the trajectory or antenna array geometry. One thing I would like you to notice is that if we use any other positioning system that could not use phase information across multiple transmissions to create a synthetic antenna array and had to use phase information across each transmission individually, it could achieve at best an error of like roughly around a meter. And this error in recreating the trajectory corresponds to a positioning error of like 4 centimeters, which is actually a pretty functional accuracy for applications like tracking virtual reality accessories. I also conducted 100 similar experiments where the target device is uploaded from the access points through walls or furniture. And the system performs, the system has comparable accuracy even in these environments, and of course it shouldn't come as a surprise as these obstacles are essentially transparent for the Wi-Fi signals. And of course the system works even in the outdoor environments because we are using wireless signals, not the visible light illumination. Can we push this technology even further? So far, we have seen how we can position a device when we have multiple routers present in the environment. Say I'm at my home, I just have a single router, I still want to be able to use this positioning device. Let me make it even simpler. We all carry our cell phones with us. Ideally, I just want to use my cell phone to position all my devices for me.
With respect to the cell phone?
Yes. So the cell phone would act as the anchor point or the origin of the positioning system. Yes. Now that way I will be able to play my virtual reality games whenever I want, wherever I want, without having to worry about the wireless coverage and so on. And we have the necessary machinery. If we kind of like recap those equations where each set of two paths is providing one equation in terms of the underlying trajectory, we actually do not need different routers to create such different equations for us. We can use multiple paths from the same Wi-Fi device to create multiple such equations. So when I used 4 paths from a single Wi-Fi device to calculate the 3-dimensional trajectory and the 1-dimensional clock offset by applying the synthetic aperture radio algorithm that I just described, the results were disastrous. The error in recreating the trajectory quickly shot to the level of a meter from the sub-centimeter level that we just saw when multiple routers were present. So what was happening here? So the insight, the hindsight is kind of like trivial yet remarkable. So not all the objects in our environment are reflectors. In fact, that approximation is only valid for large nearby reflectors like walls. Given the centimeters level wavelength of the wireless signals, most of the objects in our environment, like laptops, they are going to interact with the wireless signals using diffraction. And remember that nice modeling that we had, where the change in the time of flight is related to the displacement in a very nice linear fashion? That modeling no longer holds true for diffracting signals. So here I'm actually showing these waveframes by using these curved lines, but the point is that although this modeling is valid for the signal that is directly coming from the router to the headset, like a point source like a router, and the signal coming from a strong nearby reflector like a wall, it quickly breaks down as we include more and more paths coming from other objects in the environment, which is what was happening when we used a single Wi-Fi device.
You just have to ask the question.
Yes.
The reflectors are good, why don't you just have reflectors?
Yes. Ideally, I would like to use naturally available reflectors rather than, but introducing new reflectors into the environment.
No, it's not actually a headset. When it's known distance, you just want to reflect. There's already going to be
Yes. So actually modeling these complex shaped objects is actually not going to be trivial. It is going to be like very hard to model in a tractable fashion using classical approaches. Now by classical approaches I mean that writing down equations for the forward model and designing algorithms to solve the inverse problem. However, obviously we are living in this revolution where we have these constructs, these neural networks that are specialized for dealing with these kind of hard to model scenarios. What I'm going to do is that I'm going to make this model, make this neural network learn the model. In fact, what I'm actually going to do is that I'm going to make this neural network directly output the position from the input wireless channels obtained across multiple transmissions without any intermediate steps, like estimating the clock offset or estimating the direction and so on. However, these neural networks is a data-hungry approach, so how am I going to collect this data, and how do I know that this system actually generalizes to new environments? Now, in order to train this neural network, I use this particular setup where the Wi-Fi system is attached to a Oculus system to collect the ground truth data. So the Wi-Fi system is going to collect the wireless signals, that is the input to this neural network, and the Oculus system that is rigidly attached to this Wi-Fi system is going to collect the position values, that is the labels for this neural network. And I collected 1.3 million such data points for experiments conducted across like 12 different rooms. And here are some sample rooms where we toiled to collect this data. And in order to test the generalization of this neural network, we collected a test data set using the same procedure, but in a completely different set of rooms. There is no overlap between the rooms that are being used for generating the training data set and generating the test data set. And the number of data points are approximately the same. And we trained a 3-layer 200 time step LSTM neural network to directly output the Wi-Fi position during the 200 time step using the Wi-Fi channel obtained for 200 consecutive wireless transmissions that are transmitted roughly at around like 6 milliseconds apart. That was the neural network architecture. And the major question is whether the trained neural network is going to generalize for the data collected in this test data set in the environments with the new rooms. The system actually demonstrated an accuracy of 4 centimeters on the test data set using a single Wi-Fi radio. So what this means is that information has always been there. Even if the complex shaped objects are hard to model, they still contain the information to remove the hardware distortions and achieve this fine-grained accuracy. One other very impactful outcome that we had by using this particular approach has been the real-time performance of the system. Even though I did not explicitly optimize this neural network for latency, the system actually demonstrated a latency of 7 milliseconds. And this kind of latency is actually important for making wireless positioning systems practical for applications like virtual reality, which demand position update rate of at least 60 Hz. In contrast, the super resolution algorithms that I was looking into before for separating out the signals from multiple paths and figuring out the position, their runtime was on the order of like few seconds. So what is happening here? So these super resolution algorithms, like music, they are designed to solve these complex non-convex problems. And their complexity is on the order of the universe of all possible values that the variables in the system can take. And my hypothesis, again, this is just a hypothesis, is that the complexity of this particular neural network is somehow closer to the order of number of variables in the system rather than the number of all possible values that the variables in the system can take. So I have this real-time positioning system using a single Wi-Fi device. So what did I do with it? I decided to play a Fruit Ninja game. So here I'm using a Wi-Fi chip as a hand controller, and the user plays a game using this virtual reality headset, and the image that is displayed in the headset responds to the movement of the hand controller. And the image rendered to the headset is also rendered on a laptop to show the real-time nature of the system. And the hand controller in the real world is attached to the katana or sword in the virtual world. And here we can clearly see that the sword responds to the user's movement, both for small and large movements in real time. And when the user moves the hand controller in an up-down fashion, it doesn't affect the lateral movement of the sword. Just for fun, I place this katana in a Fruit Ninja field. Now the user has to play a Fruit Ninja game where the fruits and the sword are displayed to the user, and the user has to make a judgment in real world by how much he has to move the hand controller in order to be able to cut the fruit in the virtual world. I would just like to talk a bit about the broader impact of the systems that we have discussed here. The reason I care about building practical systems, one main reason is to make them widely accessible. And in order to facilitate that accessibility, I placed my research, the code, the data, and even the ideas in the public domain. And the system is so easy to build. Go buy a Wi-Fi chip, use a publicly available software to get the wireless channel, use my code according to the documentation, and voila, you have the system. This kind of accessibility has actually helped researchers to use my techniques and compare against it. People have even built new applications like device-free human localization by building upon these techniques. And the system has not only been used by other researchers, but it has been made so simple to use that we could actually use it as a teaching vehicle for an undergrad class that I have TA. Let me tell you what we did. So we took our system, we made the students build the system, and build applications on top of it in a quarter-long project. And these are this is an introductory embedded systems class taught right here at Stanford. And it was just like so satisfying to see all these creative projects that the students have built. Two particular teams have even built a complete HoloLens application. So here, the hologram appears as if it is stationary in space because the view displayed to the user is being changed in real time because it is responding to the user's position that is being calculated by the Wi-Fi chip that is attached to the headset. That ends the technical portion of my talk. I have obviously been very proud about being able to defend the past few weeks, and that is what I've been talking about to all my friends. But as I come closer to graduation, I couldn't stop but appreciate and be so thankful for having this opportunity and to meet all these wonderful people and like to kind of like think about like how fortunate I am to be actually meet and even work with all these incredible people. I would like to particularly thank you, Sachin. So it was just a very special relationship, and yeah, there have been like professionally and personally setbacks, but thanks for handling me throughout all the situations. And I'm really owed to this particular thinking process I have about this affinity to bring this like to kind of like concentrate on the practicalities of a particular system. I think I kind of like learned it from you. Thanks a lot for that. Yeah. Victor, it's a really it is like you're the pioneer in this field, and it actually means a lot to be able to present this dissertation. Thanks a lot for being on my committee. Balaji, I always enjoyed the stories, the classes, and all the exciting discussions that we had. Thanks a lot for the collaboration and for being on this committee. Gordon, it is actually when I was taking the computational imaging class with Gordon that I started this virtual reality Wi-Fi tracking project, and that was a point that I realized these connections between computational imaging and what I was doing. Thanks a lot, and Shreyas, it has always been incredibly inspiring talks with you, and thanks a lot for guiding me through the medical project that has been for the past few months. Thanks a lot. I would also like to take this opportunity to thank Professor Ramesh Raskar. It is because of these very exciting discussions that we had that we kind of like realized these awesome connections between the way we think about cameras and the way we think about radios, and I'm really psyched to push that particular direction forward. And I would also like to thank Ranveer, who has been an incredible mentor, especially during the early years of my grad life. I would particularly like to thank Kiran and Dinesh, both of you who have kind of like mentored me during my first 1.5 years. They taught me the practicalities of the wireless system. They made me realize that whatever you learn in theory actually works in practice. That is an amazing field to have, and thank you, Kiran. And during my first few years, it has always been because of the mentors that I had in my lab. Pengu, Manu, Dinesh, Rudy, thank you all for mentoring me through my initial years at grad school, and still continuing to mentor me. Thank you. And these people actually set me the role models for me to actually mentor the grad students when I got a chance. Thanks a lot, Samuel and Colleen. And if you would like to thank anyone for all the samosas and chai that we had today, thank you, Samuel, for taking all the responsibility. I would like to thank all my collaborators at Stanford, MIT, Microsoft, for all the projects that we have done during my grad life. And I would like to particularly extend my thanks to my family and all the friends here. Like, without you guys, few particular decisions would have been extremely difficult to make in my grad school. You all folks, thank you all for being here, and I really can't thank you enough. Thanks a lot.
Wonderful. So we have time for a few questions.
What were the inputs to the neural model that you were using, and do you think that's the way to go compared to the extra radius I could add for better accuracy?
So I was using a Wi-Fi system. So in a Wi-Fi system, the signal is transmitted on multiple antennas, received at multiple antennas, and it is transmitted on multiple frequencies. So in the particular system that I built, I used 3 transmit antennas, 3 receive antennas, and 30 frequencies. So it was like 270 complex numbers per transmission, and I used 200 such transmissions. Okay. So this is the input that I am feeding into the neural network. So,
and that provides you the position of the object at every point of time, or the displacement?
It provides the position, the output is the position of the object for the 200 transmission. So it is kind of like converting a sequel to a stream kind of like system where you continuously get the output positions for like 200, and so on.
So just continuing on that, you said it generalizes well. So did you even test it on environments which you have not seen? Because in the slide you mentioned that the train and the test data sets were from the same room.
No.
So they also generalizes too.
No. So the training data set was collected in a set of 12 rooms, and the test data set was collected in a set of 11 completely different rooms. So there is no overlap in the rooms where the training data set and the test data set was collected. So there was yes, please.
If there are humans or other moving objects in the room, how does that impact your work?
Yes. So one particular assumption that we make in the modeling and everything is that the environment is stationary and the only moving device is the target device that is creating the synthetic antenna. So having other objects moving, like the moving humans, is going to have a mismatch between how we are modeling the world behaves and how the world is actually behaving. That kind of like contributes to the errors in the system because we do not explicitly account for that. However, if we can account for that, it would actually be better. We cannot overcome that though, because all these experiments are conducted in like as the people were moving naturally in all these environments. So it was.
Right, well, I think the environment of VR tends to be in a room by itself, and so I think that's the privacy.
Yes.
So, going back to the same thing, so do you think, your model generalizes over different devices? If you train the model on one particular device, do you think you can just apply the model? Then in that case, you don't have to worry about the environments.
That is a very important aspect to the system when we consider the practical deployments of the system. We can give a very confident answer to that question once we can empirically test this on different devices. What we are using is the wireless channel information. Now, what does that wireless channel information depend upon? It actually depends upon the antenna too. So, how much does it depend? How much it is going to affect? What is going to be the generalization accuracy of different devices is going to be a very important question. And
Actually, I have a follow-up.
adding to that, yes.
Sorry, finish up.
Adding to that, like the distance between the antennas is also going to be a pretty important factor. So the different devices have different distances. So how do we account for these different antenna geometries in different devices? Different antennas in different devices is going to be a pretty important research area as we push this towards the system.
So it's a similar question, but so most of the places where you apply any kind of new networks or CNNs or anything of that nature, if you perturb the input, you're not going to get the same result. I mean, in the sense that you sort of have a different kind of input. Even though you did this experiment in different rooms, from way back when when I was doing this sort of thing, but I remember that even when you used a chipset from the same manufacturer, the results were different. Like the RSSI or the CSI that you captured was actually different. So because the chips themselves had variations in it. So the question I have is that when you did the experiment, you used the same device and the same chipset rather than different ones, correct? So how confident are you that if you actually use a different one, which will actually change the kinds of environment you're doing, you will still get the same localization? Because that's reality, right?
Yeah.
Everybody has, even if they have the same program chipset, it's not going to be able to happen.
Yeah. So how confident am I about whether the system working on a different chipsets? Now there are two aspects of the system. One is the signal processing aspect when multiple routers were there, and the neural network based aspect when we only have access to a single router. Now when multiple routers were there, those experiments I kind of like conducted experiments across multiple chipsets. Like I have worked on it for like multiple years.
So actually I was more concerned about the single route case.
So that experience kind of like suggests that it is somehow like the signal processing algorithm is somehow not getting affected by the variations in the different chipsets itself. Now that is the data point I have. Now in order to confidently answer this particular data point, how a single Wi-Fi device with a neural network trains across multiple chipsets, we have to conduct an experiment. But the data point I have is that it was not that sensitive to the signal processing.
The situations are different.
Yeah.
When you did the multiple router thing, you used music.
Yes.
That's an exact set of equations and so on. Whereas when you're in a single device, you're using neural net, that's this question actually.
Yes.
How does the neural network generalize across devices? And I think, that you're saying you have to just check it out. But a related thing is, what if you have these 12 rooms? There's a training set is sort of determined by you as a useful set of things. Then, for every device that's made, a headset, just run them through this and obtain the data.
Can you please repeat that last
So
statement?
take a device,
Yeah.
just manufacture.
Yeah.
Take it to 12 rooms. put the device through the paces, collect their 1.3 million data points, etc. And that's the training set for that device. Burn it into the neural network, ship it. That should work, right? In principle.
Yes, it should work in principle. Victor kind of like raised a point that even different Wi-Fi chip, different hardware from the same Wi-Fi chip maker with the same Wi-Fi chip, they still have like differences. I think that's what.
Oh, I see. Not the
Yeah, so
headset,
we take
not the receiver side.
You take a different client to a different, so what he did was he took the same hardware that he collected the experimental data or training set, then he went and collected another set, but used the same hardware. So my question is, you use a different piece
Which
of
hardware are you talking about? Talking about the Wi-Fi?
So, yeah.
Or you're talking about the receiver and the headset?
Both the chips.
No, but the antenna spacing and stuff you talked about. That's more for the receiver.
Yes.
That's what I'm saying. The problem is more receiver based, you can train.
For each particular device type, we can train a neural network and burn it into the device itself to create a positioning system that is customized to that particular device.
Right.
That is.
I think I'm just fundamentally like, I'm very skeptical about anything to do with neural networks. We can't really explain what the heck happened. So that's it. So I mean, I understand your answer, but I think your answer, as far as I've internalized, is that you have a pretty good view to it, but you haven't actually done that particular test of taking a different device and then trying to match it. Very good. Okay.
So before we go to the closed session for the committee members, are there non-committee members that have questions?
I have a quick question that is similar to Lisa's question. So is your algorithm and model also sensitive to like new devices coming into the environment, say someone? Okay.
Yeah. So in Wi-Fi systems, when a particular device transmits, the rest of the devices they do not transmit. So due to medium access protocols, like even if there are like multiple devices, they just kind of like the system is designed such that the communication system itself is designed such that they do not collide with each other, and so whatever the wireless channel information you get, it is kind of like from a particular device. So that.
Did you check if your model is susceptible to diffraction issues that you had with your original algorithm? Because I love the idea that using my phone, just put it over there and start playing.
Yeah, so the reason why the system was actually working because it was somehow internally accounting for those effects by looking at the data.
But you said if I use one transmitter, I'm getting this diffraction effects because. So you're saying that the model.
Yeah, we are using a single device. So.
Also, that's awesome, right?
Yeah.
So if I work 1 year on trying to improve this model and make its accuracy as good as the model-free algorithm, I can actually ship it.
No other questions? Okay, well, let's thank the speaker again. This concludes the open session. The closed one will resume.